Yeah, we just go like that. Right, what we're going to look at is the easy sum. So what we've got here, this will be the agenda. Safety of the system, overview. I've taken the cable parts out. I did have a section in there about different types of cables, but I've sort of taken that out because you guys, you don't really need to know that sort of thing. Types of faults, tracing of cables, fault location process. So the main thing we have to worry is always follow your company safety rules. You guys should know this inside and out. Ensure the cable is de-energised and grounded before connecting. The three sorts of capacity voltage you have operating voltage, approved bed, then ground the cable itself. Induced voltage is something that can happen when we have cables running along it. You guys are aware that if you're not earthed, if the cable you're putting on isn't earthed to the ground, you can actually get an induced voltage through. So make sure it's earthed when you connect the system up.
Do you think the guys should actually record this as well? Then they can do a playback at a later date, just in case we need to clarify anything.
That's what I'm doing. This is Paul. That's Andy.
You doing that, are you, Paul?
Yeah.
And then you've got another hazardous voltage we have, the actual unit itself, in terms of DC source. So the capacitor in it, it's got its own high voltage system built into it, so you have to be aware that the unit itself generates high voltage. This is basically the connections. So this is the unit here. This would be the phase, so we connect to the phase, and this is a HV return. Now the HV return wants to be where possible to the earth closest to the HV connection. So if possible, the sheathing or where the sheathing is connected to. And then you have a protection earth unit, which will go to the substation earth. Now, it's not always possible, we understand that. So if it's not possible, you need to get it onto a good ground. Because this is where the systems come into problems, where we've had people not grounding the unit properly. And then what happens is whatever voltage we send out goes through here, then comes back. Now, if we're not grounded to earth, the voltage has nowhere to go. And it can damage the unit in here, but also the operator itself, because you've got a built-up voltage that you cannot put down to the general mass of earth. The unit we have, and I believe all the units you have now, have this system called FO. It's basically between this point here, this protection earth point here, and this HV return. It has a 5 ohm difference. If it goes above 5 ohms, the unit will not work. That's basically saying is that the systems aren't at the same earth potential. And once you start going above 5 ohms, you can start then going into potential differences in voltages, and that's where injury can happen. People can get shocks because there's a potential difference. So the safety system will not allow the unit to work. If you have to frig it, there's something not right somewhere. You'd have to have a look at your earthing systems. Right, with a quick overview. We know every fault is different. There is no magic formula. You know, you'll often hear people call fault finding a dark art. It is in a way, because every fault you go to is different. You have exactly the same cable, laid at exactly the same time, running in the same pit, and they could both fault within 6 months of each other, and they could both be different. You could have a high resistive fault, a low resistive fault. So the art of fault finding is looking at the fault itself, taking everything in about it, length of the cable, type of cable, how many joints are in the system, is it a high resistive fault, is it a low resistive fault, can it hold a voltage, does it not hold a voltage, and then from there you sort of make your mind up on what piece of kit you would like to use on it. You know, we know that for a TDR or a Teleflex you need it less than 200 ohms. If it's 500 ohms, you wouldn't be able to use a surge generator purely because we wouldn't get a charge for cable. So then we have to start looking at bridges. So looking at the fault, getting information about the fault, gives us then the best possible way of finding where the fault is. So the below process works most of the time for direct shielded cables. Trace the path of the cable. This is the biggest thing. If you don't know where your cable is, if you don't know where the lay of the cable, it doesn't matter how good a fault locating equipment you have, you will never find your fault. Because if you do a fault location and your fault is 380 metres from you, but you don't know where the cable's running, you don't know where that 380 metres is. You've got a big circumference of 380 metres from your point. So tracing the cable is one of the most important things you will find to find a fault. Do a breakdown test. Now, we do a breakdown test purely to look at how much voltage the cable is holding. If the cable holds good voltage, we know we can get a flashover, we know we can get a good reflection back, and from there we know we can get a good pre-location of where the fault actually is. And it also tells us what to start setting the equipment up. Because if you're using one of the bigger units, like you guys have in the van, 32 kV systems, I have a 32 kV system sort of in the workshop with me, you don't want to be putting 32 kV down a cable if it's only holding 4,500 volts. We would reduce that down to say 6,000 volts, because we know it's enough to break it over the fault itself and not any spurious voltage running up and down the cable. If we put 32,000 volts down it, yes, it's going to flash over at 4.5. Some's going to go down that 4.5, but we're going to stress other parts of the cable out. So doing the breakdown test is very important so we know how to set the equipment up. Then we do the pre-location. So once we've done a breakdown test, we've got the 4,500 volts as the breakdown voltage. We then do the pre-location. So with the Easy Thump, it's got a thing called arc reflection. And it basically sends out a TDR pulse. You get a rough idea what the cable looks like. Then it sends a TDR pulse out. At the same time, it sends a little high voltage signal out. And because we've set the unit up slightly above the breakdown, it gets a little flashover. And for that fraction of a second, we get zero impedance to earth, which will give us our pre-location. Then we go to pinpointing. And this is where we sort of thump the cable, get with the digiphone, get the guys to the 430 metres. We had a pre-location. He rings up and says, can you start pinpointing? And then you start thumping the cable. So look at different fault types. This is common with aluminium cables. The fault has burnt open the conductor. I don't know if you can see here. It basically blows a hole in the cable itself, and it sort of splits the cable in half. This sort of fault, easy to find with a TDR. As long as you've got a good core to compare it with, or if you know your cable's 2 kilometres in length, and you get an open end at 800 metres, that's obviously where your fault is, because it's just blown a hole straight through the cable. See, the TDR cannot see past this fault, so that looks like the end of the cable. You may not be able to thump it. The way you can thump it is a bit unconventional, where you would go on the good core, and then what you would do is you'd link the good core to the bad core at the other end. So basically you would thump between what looks like two cables, and then you can get a thump fit in certain circumstances. But usually you could see it with a TDI and you have a good idea where it is with your velocity factors. This is normally the ones that predominantly we'll see. If it's not a joint gone down, it's usually a pinhole. It's just where either come from a water tree or electrical tree, the insulation's broken down a little bit and the voltage has gone straight through the insulation, makes a tiny little hole, it carbons up, and that's what causes the fault. Usually high resistive because it's a very small hole, say typically greater than 1,000 ohms, high breakdown voltage. This is perfect for arc reflection. The centre conductor is continuous, but not in contact with the outer sheath. So this is where you will see a perfect looking cable on a TDR. this one was near a termination. But this is sort of one where you get the perfect trace of the TDR, you then send a little bit of high voltage down, and that voltage will go through the pinhole and it will flash over. Centre, conductor and neutral in direct contact or shorted with metal. This is mechanical damage. Something's gone down the side of this cable. If it's less than 100 ohms, this is TDR. Again, it won't see past it. Some people will not produce noise because there's not enough capacitance in the cable to charge the cable up to get this ball of energy to explode. Arc reflection may not be possible. When you've got 100 ohms or less, I would generally say your best friend's your TDR. Get your TDR trace on there, do a trace on a good core, and then do it with a bad core. And if you overlay the traces, what you will see is there will be somewhere where there's a huge difference between the traces, and where that point of separation starts is a good starting point for your fault. With these sorts of things, you will generally go to that point where you've got a good pre-location, your 430 metres, and you will very possibly see a new signpost, a new bit of tarmac on the ground, a new fence post. You'll see some sort of evidence that the ground's been disturbed, because this has been caused by mechanical damage. Tracing the cable, I think this is one of the most important things with fault location. It allows us to see the cable path, so we know where the cable is running. Can help avoid pitfalls. You want the guy walking, if you set the guy to 430 metres, you want him on the right side of the street, or you want him in the right street, you want him in the right car park, or the right corner of the car park. Because if he's, 20 metres away, he's not going to hear the thumper going. He's not going to be able to pick up any magnetic or electrical pulses. So you get him on the cable, you've got a lot more chance of finding where the fault is. Loops, bends. I remember many years ago in the UK, there was, I believe it was a street lighting, all went out to a load of contractors, and they were paid by how many metres of cable they put in. And what they were doing is they were looping cable at the bottom of lampposts. So if a lamppost was 30 metres between lampposts, they could have 50-metre cable there. So when you got your fault, you couldn't know where it was, because the actual loops that they just chucked down somewhere was making that cable length look longer than what it was. Again, with bends, if you run a cable up the street, how tight a radius does it have? Does it go all the way round? Has it been diverted around the other side of a roundabout? So you're looking at all these things and ditching the cable as well. If you have a lot of your cables going up over gantry systems, over motorways and train tracks, across the actual motorway, the train track, maybe 50 metres. But by the time it's gone up 10 metres, 15 metres, then gone across and come down again, the length of the actual cable could be 50, 60 metres longer than the run itself. Unexpected route. Has had a divert. I worked on a cable where they stuck a new roundabout, diverted the cable, and it ended up on the other side of the street before it crossed over again, and it wasn't updated on the drawings. So we thought it went one way around the roundabout, or way across the roundabout, because that's what the original drawing said. But where the new roundabout was, they actually diverted it around the side. So we didn't know where it was. So we had to do a trace of the cable to find out exactly where the route was. So with arc reflection, ARM stands for arc reflection method, gives cable meter distance to fault. So it tells you how far down the cable the fault is. It doesn't tell you where the fault is on the map. All it's saying is it's 430 metres from you. Where that 430 metres is, this is why you need to trace the cable to find out the route of the cable and where that 430 metres is. Again, see, it may not be in a straight line. If the correct cable route is not known, then it doesn't matter how good the pre-location is, it will be virtually impossible to find the fault. So we know our fault's at 1,200 metres along the land, but where the cable's gone into the ground, you could be tens of metres away. You could be 20, 30, 40 metres away. So we start. So the initial setup. So we have a fault on L1. So L2 and L3 are grounded. We set the easy pump up, HV through the core, and then the HV return come back through the sheathing. A high pot test. When you switch the easy pump on, which we'll go through later, you will come up with the initial screen as it starts up, and it's very intuitive, the E-Tray systems, so it will take you to the test it believes you should do first, which is the high pot test. We want to know what this cable breaks down at. So we set the voltage up, it tells us to push the green light. Then it will charge the cable up and it will flash over. And once it's flashed over, it stops the test, tells you what the voltage is, then it will immediately take you to fault location. The high pot test. And that's our flashover. The unit immediately stops, gives us the voltage. So pre-location. Once the high pot test is done, it immediately takes us to fault location. The first thing it does is a TDR trace. What it's looking for is the end of the cable. And it doesn't know where the end of the cable is, but what it's looking for is the highest impedance change it can see. Because generally, the highest impedance change it can see across the cable is the end of the cable. Because if the cable is either in cable earth or the breaker is open, that's the highest impedance change it can see. It'll either be infinity or it'll be zero. So unless the cable has been cut or so severely damaged that the trace can't go past it, you should see the end of the cable. Then you can refer to your drawings. If our cable is 2 kilometres, then what we should see is an open point or a short circuit at about 2,000 metres. So, cable end most likely at 940 foot. So we confirm that. So there's our TDR trace. Just runs through. Can't see the fault because it's too large an impedance. So what we're going to do is we're going to set it up, the voltage we need, and then what we're going to do is send this little pulse down, which gives us zero impedance for a fraction of a second. And that's where our fault is. The beginning of the separation, just here. As the separation starts, that's the position of our fault at 1,200 metres. Right, pinpointing. You guys are familiar with the Digiphone, so we'll just have a quick run through this, just in case you can pick anything up from it. This is something used for acoustic pinpointing for core-to-core or core-to-shield faults. Why do you use a pinpointing device? Reduce the duration of direct surging significantly. Many years ago, I'm not sure if you guys remember, but a lot of people years ago, before we had the likes of arc reflection, ice decay, that were very popular to use, a lot of people would either cut the cable and keep testing until they found the section it was, and then they would just thump it and walk it until they found where the cable was thumping. They wouldn't have a pre-location, so they were just using a ground mic, a Digiphone, just to walk the cable. And all the time you're doing that, you're stressing the cable. So if we can get you to within 20 metres of a fault, and then you can pinpoint using a good ground mic, you should be able to get onto the fault very quickly. This way you save any future faults appearing. So weak joints or weak parts in a cable, you're not actually stressing. The start pinpoint based on the TDR results. Acoustic techniques can be misleading. Steers the user to allow the sound. This can be inducting, either in the plastic ducting we use a lot nowadays for solar farms and wind farms, or the old concrete troughs in what the rail companies use and some of the older cables are laid in. You can get an echo through it. So we tend to use magnetic and acoustics. Again, getting the right point to dig up. Digging a road up.
Tony, just hold on a second. Tony, just a question for you there, if that's all right.
Yeah.
Is it common for the magnetic trace to leak out the end of the duct? And is it common for your magnetic trace to get to the power point at the point of connection from the broadband or the power of the generator?
Did you hear that, Tony?
I heard something about the magnetic trace at the end of the duct.
Yeah, just Sam says, is it a common place for the magnetic discharge to be at the end of the duct rather than the falls? Yeah. And what was the other one, Sam?
No, the acoustic would be the end of the duct because it travels along and echoes through the duct.
Sorry, the acoustic
is magnetic pulse. There is a slide, I think, after this one that shows you the magnetic come out. The magnetic will hit it first. It's like thunder and lightning.
And you go through the coincidence measurement then as well.
That in a minute. It's the acoustics that causes the issues because once you're in ducting systems, it can echo. So it sort of echoes through the whole conduit, the ducting system itself, and that's what causes the issue. That's why we tend to use the magnetic and the acoustic. The magnetic sometimes can be shielded, which can cause problems, but by using the more advanced systems we have now are so good at picking up the magnetic pulse that even in ducting systems we would go by the magnetic. I don't know if you guys have been out with me when I've been fault finding and done some training in Ireland, but I always tell the guys that don't listen for the sound. The sound's the last thing you want to hear. You want to look at the magnetic.
Yeah.
And the way
sorry, Tony, there's just another query that's just Sam wants.
The numbers of the magnetic trace that are on the listening gear that have gotten them lower at the end. Now, rare, but it has happened. Not the acoustics coming out. I know that.
Yeah. They're saying that the magnetic discharge tails away at the end of the duct. Is that what you mean?
It's lowest point.
But that's and that's easy to see, and you'll cover that, Tony. Yeah.
Yes. What you get is with magnetic. So it sometimes can be masked depending on what the ducting systems are like and how many cables you've got in it, and there's a lot of variables with this. But generally, we are looking at the magnetic more than the acoustic. The acoustic is always secondary because you can get, not just in ducting systems, I've seen on a cable that it was on a pole termination where the fault had gone, but the sound was resonating through the shielding systems and they were picking up the clicking sound about 150 metres away from the actual pole termination itself. So the acoustics can be quite deceiving sometimes. And the human brain, you want to hear that. You know you want to hear that sound. And the brain can sometimes fool you to do it. That's why we always go for the magnetic, looking at the numbers.
Right. Yeah.
This is what we go back. So the thunder and lightning, which comparison in the time domain, the time between the electromagnetic detection and the arrival of the sound wave, this is what these little numbers mean on the digiphone itself. So when the magnetic hits the listener to when the acoustic hits the listener, this is what this time is. This is why we look at this period of time. The closer we get to the fault, the smaller the numbers become. And I won't generally put on a set of headphones until it's less than 20 milliseconds. Because more above that, you can't always hear it, but your brain will want you to hear it. So you sometimes sit there and think you can hear it. See, the first sound, not the loudest sound. And magnetic isn't easily fooled by the conduit. So pinpoint, minimise hunting times, reduces stress on healthy cable, leads to increase on overall system reliability because we're not stressing the cable. Less time outside, you know, if you're on a cold, horrible, wet day, the sooner you can get to where the actual fault is and put your cross down, the easier it is for you guys. Reduces the guesswork, got your pre-location, you've got the guys out there 10 minutes instead of 3 hours. Definite indication of progress. Again, not fooled by concrete or conduit or concrete. This is where we're looking at this magnetic and acoustic pulses. No overshoot. Indication of past the fault. If you go past the fault, your numbers start going up. And depending on what the fault's like, a lot of the energy goes through the fault. So the further away you go, not just will the time get larger, but also the signal gets weaker and it will just disappear. Means you can dig a smaller trench. If you pinpointed it, you guys will know. Sometimes you can put your foot on it, you can feel it, and you know it's within, 6 inches of where you can feel it. Know exactly where the fault is. Minimise property damage and restoration costs, which we all know about, digging people's lawns and drives up. Just having a quick look at the pinpointing. What faults can be pinpointed? High resistance faults, parallel faults. So this one here, you would connect up here, and you would connect up to this good core, and you would bridge over here, so you get the pulse come either side, so it would thump here. These ones you would set up between the two cores, so it would send the ball of energy here, and then obviously to the shielding would be to this point and this point. Quarter sheath. That's just showing you a quick. And this is what we were talking about, these voltages coming out. This is showing, Sam, if you can hear me, what we're going to look at is the difference between the acoustic and the magnetic. And this is where the magnetic, this is where we can, it's a lot better through ducting systems. So the acoustics, the magnetic's already there, and the acoustic takes time to get to it. Now if you was in a ducting, it would hit there and it would run along, so you would have sound all the way here. But we still know where this magnetic is. Like thunder and lightning. You see a lightning bolt, and then 5 seconds later you hear the thunder. Even though they happened at the same time, you'll always get the old wives' tale that if you count seconds between the thunder and the lightning, you can work out how far away it is. It works. Maybe not to the accuracy that you'd want, but it works. The difference between the speed of sound and the speed of light, that difference gives us an indication of distance. Electromagnetic pulse and the sound waves flash over and travel at different speeds, so it's time-based. Measure difference on the arrival times. This is what the digiphones are, and this is where we get this 20 milliseconds from. That 20 milliseconds is a difference between the magnetic and the acoustic, and we know roughly how far that in distance that is. So we know at 20 milliseconds, we're quite close to it. I would suggest within 20 milliseconds, you're probably 5 to 7 meters, maybe 10 meters away. If you move a meter at a time, take 2 pulses, that 20 starts dying down. I found faults dead on at about 8 milliseconds, some are 10, 12 milliseconds, some are down to 3 or 4 milliseconds. So this depends on the depth of the cable and the type of fault it is.
Yes. Tony, sorry, that was more the reason I was talking about. We just call that the magnetic trace. So you get your time-based reading, so your milliseconds. I've been close to a fault, and the milliseconds reading has been higher than at the point of connection or where the duct is coming out. And I was just wondering if that common, it's very rare now that it happens to me, but is that a common thing with the gear that your lowest millisecond reading can be pointed at the start of the duct or your point of connection where your HC generator is.
Yeah. It can be, like in very rare circumstances, you can get a low reading somewhere else. But this is where we use the pre-location. If you get good pre-location, this is where we were talking before. Years ago, people would just walk the route. They would cut the cable to get the last section where the cable was faulty. They would thump it, they would walk it. Now, if we've got good pre-location, if we've got a good, this point here, where our flashover is, we've got good pre-location on that because we've got good arc reflection back. We know roughly what the velocity factor of the cable is. We tend to, with HV cables, XLP cables, the majority of our equipment is set up for 80 meters per microsecond. So we know this is a good idea. If we can get someone at this 430 meters here, the chances are this magnetic and acoustic is going to be very, very accurate. If we had to walk it, you can get resonance through it. I have seen it on very, very rare occasions. But majority of the time, 99% of the time, this time difference, this lowest point should be where the cable fault is.
Right. Thank you.
Yeah?
Yeah. All right.
Yeah.
Right, so, same as what we're talking about. The bigger difference between these 2 points, these 2 points here, means it's further away. So, the smaller the number comes, the closer you are. But always remember, if you found a fault at 4 milliseconds and you can't get lower than 15 milliseconds, doesn't mean you're not on the fault. It just means it's a different type of fault. The cable could be at a different depth. It could be different material between it that is suppressing the sound slightly, so it doesn't come up so quickly. So there's lots of variables. So don't think you've got to get to single-figure numbers to be on top of the fault. It can be double-figure numbers. It all depends on the terrain you're in, the depth of the cable, the type of the fault. There's so many variables with it. And once you get to a point, say 15 milliseconds, and you move a meter to one side, and that goes up to 16, we'll move another meter to that. If that's going up to 17, you're moving away from the fault. So go back the other way. And if 15 is the lowest number you've got, well, the chances are that is where your fault is. It's just the terrain it is suppressing the sound somehow. So this is just showing, take time in pinpointing. If you go slow and systematically, you can see here, when you get one pulse, this 66.9 will be a grey colour. When it gets a second pulse, and it's the 66.9, it will go black. Because it means, I heard it the first time, but I'm not sure. I've heard it second time now, yeah, that is it. So when you move, the 66.9 goes over to the right. Wait for another 2 pulses, and wait for it to go black. Then move again. So, I have seen some people that's got a piece of kit, they'll get a number, they bounce along. The unit hasn't had enough time to absorb all that information and say, yes, it's definitely hit me twice at 66. Sometimes you guys will know with the Digiphone, you'll get a spurious number come up, 125. Well, wait for it again. If that number disappears or it's a completely different number, the chances are you're not near the fault or you're not on the cable. It's just picking up some sort of noise or magnetic in the ground itself. What you will notice is these 2 little icons here. Now, the first one, you will see this go dark blue the way it is when the magnetic pulse, or a magnetic pulse, has hit the ground pipe itself. And then what you want is to get dark blue flash here. So that means the unit has heard an acoustic. And that's what will give us this number. And if we get the same pulse again, that number will go black. So it's a good way to identify is look here. So that's headset, you guys are aware of your mute when you touch the top of the unit, and we can set the unit up to 84 decibels. You can take that function out if it's a very, very low sound, because it's under a deep cable or it's not a high resistive fault as such. What you can do, you can go into the settings and you can make that louder. It's not recommended because it can cause hearing damage. But if you're doing it for a few seconds because you just want to confirm something and then take it back to the 84. Filters, it has different filters on it for different frequencies. This can filter out frequencies around you, or if the sound is coming through a funny frequency, you can alter the unit to accept different frequencies. Cable positioner, the new Digiphone 2, which I don't believe you guys have yet, the Digiphones you have, the orange ones, will show you roughly the position of the cable. The new one actually will tell you the orientation of the cable. So if the cable is moving slightly, so it's instead of running down the road, it sort of moves onto the path, it will actually show you the direction the cable is running. Background noise reduction, this is basically what it does is, you've heard of these noise reduction earphones. It looks at the background noise and reverses a frequency to take out some of the noise, so you lose a lot of rumble in the background. That's the last difference value. The magnetic level, the peak, the magnetic has got 2. Bar graph auto scales, so you look at those numbers, that's saying 56 and 86. If you're further away, that may say 26 and 56. And this is the difference you've just actually had. So all the time that's going like that, we know we're getting closer. Different connectors, obviously you've got your spikes for sort of soft ground, you have plates, you have a little tripod here, little domes. I tend to use this little tripod one more than anything because you get 3-point contact. So if the ground's a little bit uneven and not perfectly flat, this works perfectly. You can put a little dome on it. The sensor rod, this is for grassland. We do, I think, 150mm one as well, so if you're doing quite very marshy land, or if you're looking at some of these cables, intertidal cables, going across beaches, you can go into the sand a lot more. The green cable needs the sensor symbol, just centre of the cable.
Tony,
yes?
Tony, just, we normally use the blade for nearly everything with the lifting gear apart from grass. Is that okay? Yeah,
I mean, I tend to use a tripod for absolutely everything. I just think it gives a good point of contact. You can use a little dome. If you're going to slightly softer ground, the dome will actually screw into the bottom of the tripod itself, the little 3-pronged one. If it's on really soft ground, or you can, I don't know if you guys go through fields sometimes, you know, the grass can be a couple feet deep, you can't always get to the grass. So I'll probably use the spike then, but predominantly 9 times more out of 10, I always use that little 3-pronged tripod. I think it gives the best results generally. If you can't hear the fault, or it's very, very quiet, then you could change the attachment. If you're on soft ground, maybe put the spike in to get a bigger surface area. If you're on real flat ground, there's a big plate that you can, that's what you use all the time, yeah. The big plate sits on, gives you a bigger surface area. Depends on how you find the way you want to use it. I like the tripod because on slightly rough ground, I've always got 2 prongs at least on the ground, and it just sort of sticks in a little bit more. I do find with a flat plate, if it's quite rough ground, you don't get a good connection. You don't get a very good surface area connection to the ground itself. You know, it might be worth trying a tripod. Try it out. When you do a fault location, put the plate in and find it, and then swap the plate for the tripod, and see if you can hear any difference.
Yeah, I'll give that.
And then maybe move 3 or 4 meters either side, and again, to see if you can sort of tell the difference. It's just my personal preference. I like it because it's a little bit more universal, and the ground's never the same where the bolts you go to. Okay?
Yeah, thanks. It's not your one. No.
Right, place the sensor on the ground with the, this is another thing we have with people. This arrow here needs to go the way, the direction you're going. If you have it the other way round, the unit thinks the fault's coming from behind you, it's in different directions because it's coming against you. And if you look here, you can look at the difference in strength. When you're on the actual cable, the strength is a lot higher. So if you're slightly out, again, if you can see strength there and it's not brilliant, just angle the digiphone slightly. You can just pick it up and turn it like 45 degrees, another 45 degrees. See if the signal goes out. It could be that the cable's running at a slight angle, it's moving over a little bit. That means the sensor is to the left of the cable, the sensor is on the cable, the sensor is to the right of the cable. Right, so activate the volume limiter. As I say, it is set up to 84 decibels, but you can take that out if needed. You can put a function on, you can turn this on and off, but if you touch the handle, it actually mutes the headphones. This is designed for when you're walking up a busy street, that when you pick it up, you don't get a rush of sound underneath it. If you're in the middle of Dublin High Street, walking down Temple Bar area, you've got loads of tourists running around there, women in high heels clopping around, you've got a guy with a tango drill digging up the road. When you pick it up, you can get a lot of rush of sound into your ears. So this is designed that when you touch it and pick it up, it mutes it. So all that sound doesn't actually go through into your ear itself. And then when you take it off, it's about half a second to a second, it unmutes the system for you. Different frequencies. So this is 100 to 15 hertz. This filter setting provides a maximum bandwidth so that the flashover noise can be heard with as little distortion as possible. The distance to the fault is large and the ground is soft. The time measurement is more difficult. However, reducing high frequency can have a detrimental effect on precisely the sound characteristics of high-pitched flashover noise, hard ground, close to the fault, that sort of thing. So use a low-pass filter. Then we have a high-pass filter, which is high-pitched flashover noise, in particular hard ground or close to the fault, are not changed very much by this. And bandpass, a balanced filter setting which suppresses both low and high frequencies. However, reducing high frequency can have a detrimental effect on precisely the sound characteristics of a high-pitched flashover noise. So hard ground or very close to the fault, you don't get that bang. Again, what I suggest you guys do is when you're out of the fault, once you've found your fault, play with the different filters so you can hear the differences. You might go, well, in certain areas you might want to change the filters you have. This is just showing you your different values, your 66, your 75. Now, the smaller numbers on the right, which means you've gone past it, and the actual unit will tell you you've got to turn around and go back the other direction. Okay, guys, everyone happy with that?
Yeah.
Any other questions?
No, all okay.
This unit is, it has got FOM on it. It's a slightly older model than the ones you have. Yours is a newer model. It's got the same features on it. It's just got a different charging lead. Yours should have a kettle lead. This has a different little round connector on it. Apart from that, it should be identical. So it's basically a simulated fault. So this bit here is simulating the core of the cable. So what that will do is, it goes in there, it's got a fault. This is the HP return. So this is where the red crocodile clip connects to. This is where the black crocodile clip connects to. So in a real scenario, this would be the core of the cable or into the core of the breaker, wherever you could get. This would be the HP return. So this would be either the earth tunnel or the breaker, or at the back where the sheathing comes in. The closest point to the sheathing as possible, and this here is simulating our substation earth. And if we look, if you see the sedge lead here, this lead here goes out to an earth spike I've got in the ground outside. So what I'm going to do is this crop clip I'm going to attach to the earth point. This simulates now that I'm connected. This is general mass of earth. The first question is next.
You want to plug that in?
Yeah. Is this braided cable. This is the protection earth. So all we have now is this cable here is connected to our substation earth in our substation, or if we're on site somewhere, an earth spike, something to the general mass of earth. Then the black lead goes to the HP return. So this here is the nearest earth point to the sheather. So if we can get on the sheath of the cable, that's where we want to be, or in the earth tunnel of the breaker, where the cable comes into the breaker, anywhere where it gets very close to the cable. Then the red here. This here is simulating our core. So this would be the core of the cable if you open a breaker up, one of the face tunnels. So we'll switch the unit on. So the unit will boot up. Now we've made all the correct connections. The unit should fire up. This is a bit. Turn that brightness down. Yeah, I can turn the brightness down here. You can see that. It's not brilliant. What we have here is test. Start through one by one. So it says that that's the TDR, pre-location, pinpointing, and burning. Take it back to hypo. Now, if we switch the unit off. Right. What I'll do is I'm going to disconnect the earth.
If we show him on this, then it would be better if you go through on this one.
Yeah. Only if I take the over the bite on it go through it, it's slightly different than one you're showing us.
Yeah, mine may have more functions on it.
Yeah.
Yours possibly only has 3.
Ours has 4, Tony.
Has 4.
So there we have the high pop, CDR,
Pre-location and pinpoint.
locate. That locate is pre-location, is it?
Locate is pre-location. What we'd use, if you just wanted to do a TDR trace on something, you would go to TDR. When you do your pre-location or your location, that's where it will do a TDR trace followed by a high voltage pulse.
Yeah.
Okay? Now, if I disconnect this I'm now simulating not having the earth and the HV return at the same potential. What the message I would get up would be check FOAM.
Yeah. That's what we got here, yeah.
If you press OK on yours, so press the little white dial down.
Oh, you've done. Oh, okay. Check FOAM.
Right, press again.
Click it again.
Just click it again. See?
Yeah.
Check FOAM. What that's saying is the brass braided lead and the black HV return are more than 5 ohms apart. This is purely because you haven't got it connected to anything. Mine is, I've disconnected the earth braid from the earth system. Now, let's back up. And press OK, it clears it. So now I know now that my 2 earths, my protection earth and my HV return, have less than 5 ohms between them. You happy with that?
Yeah. Yeah.
Right, we can do a little high pot test. So on this one, on my one, I have a high pot, and the icon, the next icon to it. No. Yeah. Right. Take up to 12 kV. Right. Press OK. Now, what you would do is you would set this to the maximum voltage you'll have down your cable. Right, press the green button. Press the middle button. No, the dial. There you go. So what it's basically saying is you can't get any more than 300 volts out of it. So you press OK. So just press the dial down again. And it automatically goes to fault location. So what it's saying is, it reckons the end of our cable's at 124.6 meters away. So what it's seeing is the largest impedance change is about 124 meters away. Now, if on my cable was 500 meters, I know I've got a problem at 124. So the chances are that there's been a break in the cable there. So if we accept that, say yes, we're happy with that, and what we're going to do is we're going to do a locate. So we know it didn't hold any more than 300 volts. So 2,000 volts is fine. So if we accept that, press the green button, start, ramps up, press the circle button again, and it releases. And it's not very clear. You guys see too live. Let's see if I can just try bring it right down. No, can't really see that very clearly.
Yeah, see that now, yeah.
You see that now?
Yeah. Yeah.
And that's what we're looking at, separation. So what we've got there is the blue trace is our reference trace, and the red trace is where we set the CDR trace and high voltage signal down together. So when we've had that fraction of a second, zero impedance to work, it's giving us this little bang. And that's where our fault is. Okay? Right, and if you accept that, it will then go to thump. Now I won't thump because my test kit isn't designed for thumping. It's designed to do a pre-location. It's got small resistors in it, and if I thump it, I'll blow it up. So basically, what we do from here is
No TDR. You can't tell
Yeah, not testing equipment.
Nobody even put the lead on it.
Cable.
You won't go push the lead short now.
No, it takes into account the distance of the lead.
Get your part, yeah. You're only starting for the front of the lead automatically.
Oh,
You don't have to the lead.
See, the van has TV.
Yeah.
This removed the red clap over the heavy car and give it a clean.
Yeah. And you can compare the two.
And we compare the two now, yeah.
You have to move the focus or the line when they just override each other.
You'll see the split. You see the split automatically, yes. So you don't. It's one of the. We do this opportunity. Yeah. Take one down the head and the bottom.
Yeah.
And I'll see a separation.
Use it remote.
Yeah. But that is on. That is still the.
Did you mention to about the power needed?
No.
Yeah.
I think the package in that now it's much higher.
Yeah.
what I'm going to do is I've seen a spark gap. Give you an idea of sound. Hopefully, spark gap's big enough.
You can't check voltage method.
Yeah, no, that's all right.
You really want to be the best.
Yeah, right in the feed, yeah.
No, I just.
Yeah, me.
Yeah.
Yeah. You're heavy. This, yeah, that's 20, 30 kilos. Yeah, you know the generator and the valve? Yeah, that's out there. Yeah.
Lovely.
Are you ready for this, guys?
3 days down these seven shops. Just get a look at that.
I've just seen the spark gap. Hopefully it's big enough.
The pulse is coming in slow around. Down with the cells up, yeah. So
We're looking at around 9 seconds.
you could set the discharge from the battery. Yeah. But that will be a lot slower. We won't get the same pulses per minute and that. Yeah. Tony, I think we've lost your sound now.
You've lost what?
Oh, sorry, I don't know if you're talking there. We couldn't hear anything.
Yeah, I'm just letting a spark gap for you. So this is how we would thump. It makes us the thump.
Yeah.
So what it's doing is it's taking us to the desired voltage and it's charging the capacitor up. So can you hear that?
Yeah. Yeah, you can, yeah.
We'll let it go one more time and then we'll stop it. And that's it. And it's that simple to use.
All right. Yeah. You're sitting down the road with the mic, you know, with the electrical one, and it'll be a while, you know. Even if you're trying to pinpoint it, like, you're going to be a lot slower, you know. The phone will be hopping. Yeah.
Have you got yours set up? Do you have any problems with that, or are you quite happy with yours?
Oh, okay with that. Grand. The voltage, running voltage for us is plugging in what we need for it.
Yeah. Just the power that'll take, Tony, what kind of Jenny would you need, running time for it? It's battery charged, is it, yeah?
Battery in it, yeah.
Yeah, the only thing I would say is if you're going to run it off a Jenny, it just needs to be a good Jenny. It doesn't need to be really powerful. Yeah, it's just if it's like these cheap Jennies that don't generate a good sine wave.
Yeah.
It can struggle to charge the capacitors because it uses a lot of power on it. But a normal, I don't know, 2 kVA, something like that would do quite easily. In our test band, we only use 5 kVAs or 7 kVAs for the big ones.
What's the power output of that, Tony, that unit?
That's 500 joules.
500, right.
Yes, 500 joules. This here is 12,000, so it's an easy thump version 2, 12 volts, 500 joules.
Right.
So at 12,000 volts, you have 500 joules. But what you will get is half voltage is a quarter energy. So if you drop this down to 6,000 volts, you're only going to get about 125 joules of energy.
Yeah.
So the one downside of the easy thump, well, the 12 is it's only a single capacitor.
All right.
We do we do a dual capacitor one, which is 3 and 1.5 kV. This is more for the elderly networks. And the test bands and the bigger units, they tend to have either 3 or 4 capacitors. So you get maximum energy at different ranges of voltages. But then the more capacity you have, the bigger and heavier the unit is. The thing about the easy thump is it's designed for portability. You know, to run it off batteries. And you can quite easily, if it's a new unit, run it for the best part of an hour thumping before the batteries cut out.
Right.
Now, if you have to thump a cable for an hour, you've got to rethink what you're doing.
Yeah.
I always say to people, if you thump for more than 10 or 15 minutes, switch everything off, go do your pre-location again, make sure your pre-location is the same, we're at our 430 metres, and make sure the people that you've sent there are at the 430 metres. Again, we look at this lay of the table. Have you measured it out correctly on your map? So, have you measured your 430 metres and it is where you sent the guys, or are they 100 metres away? Have you measured it slightly wrong? If you have to thump for more than 10 or 15 minutes, the chances are you're not very close to where that fault is. So, you go back and rethink it. People that thump cables for 20, 30, 40 minutes, all they're doing is stressing the cable. And in the process, what you can do is you can lose the resistance of that fault. So the more you thump it, the more that resistance can die down. And the thump will get less and less, and you'll end up almost with a dead short. So,
What's the time, Tony? What's the charge time for that from dead to?
we just tend to keep them on charge overnight. If you went out during the day, the guys used it a couple of times, 3 times, get it back to the yard, stick it in the tool room or wherever you keep your tools, and just stick it on charge. Just let it trickle charge and take it out next time. You can run it from the mains as well. So if the battery does run out, someone did forget it to plug it in overnight and charge the batteries, just run it off the mains. Run it off a little generator. I don't know if you have... sorry?
And you get the lithium-ion batteries in it?
Yeah, it's got built-in batteries in it. What you will find is after 2, 3, 4 years, depending on how much you use the unit, it may not hold the charge as long. So instead of being an hour, it may be down to 40 minutes. So
is it designed for permanent cycle charge, Tony?
To charge the batteries?
Is it designed for permanent cycle charge, or should you just charge it and switch off? Permanent, yeah.
And then, Tony saying we have inverters in our van. So they run at a max of 1,000 watts. Would it be okay to charge the unit off the inverter?
Yeah, you can charge off the inverter. But if you've got them in your vans, I would suggest just run it on the mains. If you've got inverters in the vans, it doesn't make any difference. We tend to use the batteries for more remote locations where we haven't got power.
Yeah.
You know, if you can run it off mains, obviously that would be the best part for it because you're not straining the batteries. What you will notice, the little battery bar here is when it's charging the capacitors up to thumb, sometimes you'll see that bar drop right down to the 1 or 2. Now, it's not that the battery is dead, it's just drawing so much power from the battery that the battery meter in there thinks it's the battery's dying. And then when you thump, it goes back up again. So the best scenario is to run it off the mains if you possibly can and save the batteries for the more remote locations if you've got to go up a pole or you're in a remote area somewhere where you've lost all power and your substation has no power to it. I would tend to use it purely for those situations and use mains power as much as possible.
Tony?
Yeah.
What sort of distances? What's the kind of outer range at, like, you know, distance-wise on a cable?
I've found a fault with a 12 kV easy thump on the Isle of Man, and the cable was 3.5 miles. So what's that? 4.5 kilometres. I would suggest 3 to 5 kilometres is probably reaching its limit. It all depends on what the fault's like and where the fault is, because the TDR will find it quite easily at 5 kilometres plus. I can't remember what the range of the TDR is. So to get your pre-location, yes. The problem is if you start going above this sort of 3 to 5 kilometre mark, what you can get is the attenuation through the cable is if at 5 kilometres the fault is actually dead centre, 2.5 kilometres away, you may start losing the energy slightly through the attenuation through the cable. But it doesn't mean you can't put it on a 20 kilometre cable, because on a 20 kilometre cable, if that fault's, 500 metres from you, you'll see it, and you've got to thump it. So, if you do have a fault on an 8 kilometre cable, and the only piece of kit you have available is an easy thump, try it. If it's close to you, or to the other end, it's close to the other end, the chances are you may see it, and you may possibly have to thump it within its range. It's just that the longer cables, if you're more into the centre of it, the attenuation through the cable will cause losses, and you will start losing energy from the surge itself.
Yeah, thank you.
Tony, would this be, this version of the Easy Thump, would this be designed more for MV than LV?
Yes, definitely for MV. Because with your LV, you're looking at 1,000 volts, 1,500 volts. Now, you'll get a pre-location with this because you can set it at 1,000 volts. What you won't get is you won't be able to thump it. If my balance assistance puts it onto pinpoint, right, that's okay. Now, if you look, wait a minute, Aston, if you look here, that's 14 joules. So at 2,000 volts, you have 14 joules. Can you roll down that one? I've got a little software I've got on here. Try and... Try and get it down to 1,000 volts. Yeah. Right. Go to 1,000 volts. So you've got 1 joule. You can't see it there, but it's got 1 joule of energy. Now, you're never going to hear that.
No.
So this is, you will get a pre-location because you can set the pre-location up from 100 volts onwards. So you'll get a pre-location, if you thump it at 1,000 volts, you won't hear anything.
Yeah.
There is a 3 and a 1.5 kV unit. So 1.5 kV, it's got 500 joules. So that's designed for thumping more the LV networks. If you're in dire straits, but there's no reason why you couldn't put 4 kV down an LV cable. Big LV cables will take that for a few minutes. So you may be able to pinpoint if it's absolutely necessary. I wouldn't tend to do that because you are going to stress the rest of the cable. But if it is an emergency and you need to find that, yes, you could use this. You would just have to up the voltage so you'd be able to hear it. Do your pre-locations all at the lower voltage. And when you've got a very good pre-location, go to that point, have a look around, check if there's any joints in the area, check if there's any damage, any scar into the ground to see if anything's damaged the cable, and then possibly thump it at maybe 3,000 or 4,000 volts if you can hear a little click, and then you might have to turn it up for 1 or 2 thumps just to sort of pinpoint where it is. Not recommended for LV, but in certain scenarios where it's absolutely necessary, you could use it.
That's fine. Thanks, Tony.
Okay. Because the MFM10 is a bridge, so don't worry too much about the technical side of it unless you guys want to sort of look at the differences in the distances and that sort of stuff. Basically, you guys know what the MFM10 does and how it works?
No.
No. Do you know what a bridge is?
Bridge.
Yeah, not one that crosses a river. Get your brains back to your old college days. Did
Wheatstone Bridge.
Wheatstone Bridge, Murray Bridge, Cumpler Bridge, that sort of thing. It's a very, very old way of fault finding. Years and years ago, we used to use it a lot, and we'd have a bridge, and we'd have to balance the resistances, and then you would get a figure out, and you'd have to do an equation to get like a distance to where the fault was. Basically, how it works in layman's terms, without going too deep into the different types of bridges you get, you have a good core and you have a bad core. So if a good core, a cable is a resistor. So if our good core, we call it R1. Now our bad core is basically 2 resistors, because where the fault is, it splits the cable into 2 resistances. So we could call that R2 and R3. The simplest way to explain a bridge is R1 is equal to R2 and R3. So what we do is we measure along R1, take the resistance, close a little link, goes through to R3. Now that measurement, we take R1 off, so we know what the resistance of R3 is. Then R2, we measure to the fault, and we get that resistance. Now we know the length because we put the length down. So we can do an equation which gives us a ratio, and from that ratio, we can turn it into a percentage of the length of the cable. But that's in very, very basic terms. You have to have a good core, and then you can use your bad core. We've done more about
the screen. We can't see your screen there.
You can't see me.
No.
No, it's black, isn't it? What's that like? You see me?
Yeah, see you now, yeah. It's not full screen, just,
Look, you have a larger screen, that's what we can see.
Yeah.
Yeah, I've got the TV behind me. What I'll do, just so we can get on the big screen, I'll get this presentation up. Can you see that?
Yeah.
Yeah. Let's see what this looks like. Right. Okay, you happy with that? Can you see?
Yeah, happy there, yeah. You see that, Joe, yeah?
Yeah.
God bless you, Rachel. You can hardly see you.
What we're going to look at is sheet fault location and cable fault location with a bridge. Now, to do a sheath fault, it's the same principle as doing a cable fault using the bridge method. So the way we do it with this piece of kit, we can use a volt drop, and what it looks at, where the connections are, the volt drop there, it can work out what the resistance to the fault is. Don't worry about the technical side of it too much. Just understand the basic how the unit works and how we operate the unit. So the HVB is a high voltage bridge, and the MFM10 is the sheath fault locator. They are identical units. They both look like this. The only difference is the HVB has a high accuracy mode to it for looking at cable faults. I used this piece of kit over the Christmas period on a 255 kilometre cable and fast fault. So the HVB is good for 200 kilometre plus cables. So examples of sheath faults. We've all come across it. The scar in here suggests that's been some sort of spade damage or something's caught that. That looks like stones or something has gone on that, and that's obviously had some sort of score across it. All this black area here is voltage creepage. As voltage come out, it sort of burnt the cable away. And what we're looking for is these little pinholes over the course of time can cause a cable to fail. It's going through the outer jacket, but then the moisture gets in, and that's when you start getting things like water trees and electrical trees, which end up failing the cable, getting the pinhole faults we were looking at with the easy thumb a couple hours ago. So what is the MFM10? As you can see in front of you, it's robust IP54 Pelly case. Just because IP54, it's still not wise to use it in the wet. I had one from one of our IDNOs that one of their lads used it in the rain and wondered why it didn't work. Well, it had about an inch of water in the bottom of it. You know, water will get in. If you look down the sides of it, it has air vents. Those air vents are there because when the HV generators start up, it has to be cooled. So weatherproof of IP53 with the lid down. Cable capacity is automatically measured. If it exceeds the max capacity, the voltage will be limited. So the unit itself will do some pre-tests on the cable. So when you set the unit up, it will sit there for a few seconds doing little tests on the cable. It checks the resistance. You can get a thing, every once in a while it come back with loop resistance high. And basically what that means is the good core cable and the bad core cable aren't connected together. The bridge has fallen off somewhere or someone's connected it incorrectly. The resistance is too high. So it does all these pre-checks. Now if it measures the cable and the capacity is too high for what the unit can go, it will lower the voltage to get the capacitance up. So if you set the unit up at 10 kV, only operates at 8 kV, the chances are that cable has too much capacitance in it, so it needs to drop the voltage. Just one single HV connection cable. So you'll see on it, there's a red cable which has four on it, the one you have, 4 connections. Be careful when you connect this up. I have had people complain that they get the F-phone come up. The cable itself, it sits into the unit and there's 3 little notches. Now you can put that red cable in and screw it down without it actually being married up properly. That will give you F-phone. So when you put the cable in, just give it a little wiggle and make sure it drops into that socket correctly before you try and screw it up. Easy go rotary knob. It is touchscreen, but be careful because if you go close to it and touch it, you can go back screen. So just be aware of that. I tend to just use this knob for everything. So exactly the same as the easy thumb. You dial the wagon wheel round, So you've got your test, your pre-location, your pinpoints and all that. Dial it, and then the same with the easy thumb, you just push down to accept it. Again, this is battery powered. And the batteries will last all day easily. And if you do connect it up wrong, it will tell you. Right, generally about the unit. It's a measuring bridge. It's a bridge where voltage differences in two circuits are measured and compared. This is very similar but more precise than balancing bridges, which is the old-fashioned way of doing it. You would have a bridge and you'd have to balance them out. The method is used comparable to a glazier bridge. A bridge measurement is suitable for sheath faults where TDR cannot be used. TDRs won't see sheath faults, and they won't see faults above 200 ohms, where a bridge will. A bridge will see faults from 0 ohms upwards. And on the longer circuits, it can go into the meg ohms. Or insulation fault where our methods or others run into problems. Long lengths of cable, wet faults, mass impregnant insulation, resistance is too low for an arm method. The cable sheath, the jacket, protects the cable against influences from the outside. Due to damage, water or humidity can enter the cable, and the aging process is accelerated. They have done tests over the years, and they reckon a sheath fault can reduce a cable's life from 25 years to 15 years. So where a cable should, an XLPE cable, if it's laid correctly and is undamaged, should last for 25 years plus. If you have a sheath fault on it, it could be 15 years and below. In some cases, you can be looking at 5 years before you start getting failures on it. Regular sheath tests and immediate repair of faulty areas ensure the value and functionality of the cable. Basically what I have it, mains connection, you protect it first. So what you will get is, in your little bag of cables, you'll have a couple blue cables which are your bridge, you'll have a big red cable with loads of connections on it, and you have a little green and yellow protection earth cable. Again, this protection earth cable needs to go to your substation earth. It's protecting the unit and you. Your HV connection, external emergency off. They have, on the continent, there's a law in the continent that they have to have an external emergency off system. So where this little socket is here, this was on the side of this one, this is an older one, they plug in like a box which has a red and a green light on it, and there's a big emergency stop button, and that has a 50-metre cable to it. So if you're away from the unit and anybody goes towards it, they can shut it down. On-off key. So you have a little key there, the rotary button and the touchscreen, and normal emergency off. Connection effects. Negative potential at shield, positive potential at operation earth. Increase the test voltage slowly, looking at the charging current. So when you do a test on the unit, what it will do is it will start ramping up. It ramps up slowly, and what you will see is the voltage rise, and the current will rise to a certain amount. If it's a good cable, the current will rise as we charge the cable. Once we've charged it fully, the voltage will stabilise, the current will drop down. If there's a fault in it, the voltage will only get to a certain voltage and stay there. So if you set up at 5 kV and it gets to 3 and stays at 3, you'll have a high current and you only get 3,000 volts. What can sometimes happen, if it's a slight cable fault, it can actually just put a little step in it. So what you'll see is, instead of a nice diagonal line climbing, you'll see it climb slightly in a little notch, a little drop off. And that's where it's found the fault. But because the unit has quite a lot of current behind it, it can sort of push through that. Abrupt increase of the charging current, that's where the sheath fault is. Drying out the fault. What you will find is, if a cable's been in the ground unenergised for quite a while, it gets cold and damp, and if it has got a fault on it, the damp can get in. So what you will find on certain circumstances is that you'll put the unit on and it may struggle for a little while to get the voltage up. And that's because it's drying the cable out and warming the cable through. So you'll have a very high current, the voltage will rise up, and it may stabilise, but you still might have a lot of current. Now, you might have to leave it for a few more seconds, a minute or so, just purely to make sure that it's charged completely and the current drops down. Don't immediately think that it's a failed cable because you've got a high current there. It could be that the cable's been out so long, it's very cold and damp, and what we're doing is we're charging the cable up, we'll put a bit of warmth into it and drying it out. So it can take slightly longer than the 1 minute. This is a sort of test you can get out of it. There is software that comes with it. If you look in the little bag at the back, you'll find a little memory stick. The easy way, it's easy put software. If you lose it, it's a free download off the website anyway. And this is a basic sort of image you get. Probably not applicable to you guys. This is more for contractors that they'll go and test cables and they have to give a report over to the client to say, yes, we've tested your cable. That's the voltage we've used, that's the current, that's what it looks like. You've got all the cable, you've got all the information on for them. Technical data, output voltage up to 10 kV. It's bipolar. Majority of DC test equipment is predominantly negative. With the MFM10, we use bipolar. So when it does its testing, you'll see it when we start it up. In this little window here, you'll start seeing figures come up. And what it will show you is near end positive, near end negative, far end positive and far end negative. Because a positive and negative DC pulse on a cable can have different effects on the resistance. It's all to do with the galvanics of the construction of the cable, that a negative and a positive pulse have different effects on it. So you get slightly different resistances. So we do it in both positive and negative, and then we can get a better average of what the resistance is than doing either positive or negative. It's got an output current of up to 750 milliamps. You can use this as a burn function in certain circumstances. Generally, what you'll see is a 60 milliamp. All the testing you'll do is usually 5 to 10 kV, depending on the sheets you're looking at. So predominantly, you'll be looking at 60 milliamps. To give you an idea of what 60 milliamps is like, the 5 kV installation resistance you have bars, the mega ones in the big grey boxes, that has 2 to 3 milliamps. So at the same 5 kV, the MFM10 has 20 times the amount of power. What that does is, it charges the cable quicker for one, but if you've got a minor fault in it, a mix may not have the oomph behind it to show failure. It will just keep charging and charging and charging. Where the MFM10, because it's got that 60 milliamps, what it will do is it will show that fault, or if there's a weak point, it will go through that weak point because it can do it at 60 milliamps and not 2 to 3 milliamps. It can go up to 10 microfarads. The pre-location accuracy can be as low as 20 microvolts. This is the differences we look at, and that's where you can find the faults. Pinpointing, it does just like rectangular wave. So you choose what you want, is on for a second, off for 3, I think it's on for 1.5 and off for half. So you have different pulses on it. So, but we can do that up to 10 kV. You can use another frame with it. I don't know if yours has got the audio frequency on it. There is an option on these that you can have an audio frequency function on it. Battery powered, operating time, it says approximately 2 hours. You'd have to have it running at full pelt for over 2 hours to start affecting the battery. The test is so quick on these, it takes, I think it's about 60 seconds, something like that, to do a complete test. You get a good pre-location of it, you can go and pinpoint. if you can't find something within 20 minutes, you've got to revisit, are the guys in the right place? Maximum power consumption, 500 VA. Again, with this, you'll see a little copper braided lead. Now, depending what unit you've got, you may have a socket in the side here. The older ones were up here, but you'll have a little flat socket in the side here. You can charge it up from a vehicle. So if you went to the stores, your tool stores, picked it up, put it on, and the battery was at 20% or something, but you've got to drive an hour to site, just plug it in a cigarette lighter with your van on the passenger seat, and it will charge the batteries up for you. Again, if you're on site and it fails, while you're having your lunch, plug it into the car. It should be a little braided lead, got red and black cigarette lighter attachment to it. Can you see it? You got it? Yeah. Always keep that with it, because if necessary, you can charge it from a vehicle or that type of port. It should have a little black side socket, a little flap on it. Yeah? Yeah. That just plugs into there and just plug it into a vehicle. Right, we're going to look at the test itself. So again, what we're looking at is these are two different resistances. So we're just basically going to do a test. We lift the cable off of Earth, because what we're testing from is a general mass of Earth to the core. So any leakage is going to go down there and come back. So this is basically, we connect the yellow lead to the earth point with the cable lifted from earth. The cable sheathing needs to be lifted from earth. So we go from the earth side, we go into the sheathing, and what we're looking at is this circuit here. So what we're looking at,
you'll just see the multiple sheath faults, you'll just see the first one out from the unit, yeah?
What you would see on multiple sheath faults is, you would generally see the largest fault, because that's the one that's going to take all the voltage and current. If you have multiple sheath faults, what you will find is, I'm not sure if I've got it on this presentation, what you get, instead of the line going up diagonal like that, you'll get almost like a step, where it hits each different fault, as it charges it can knock it on and see it. If you have multiple faults, what can tend to happen is your pre-location will go between faults. So your highest leakage volt, if you had two faults and they were identical, the pre-location would virtually be slap bang in the middle of them. If one was a lot higher than the other, the leakage, it goes more towards that one, because that's where the higher resistance is, the higher current is. So, yes, it will find multiple faults. You can usually tell by doing the test if you have multiple faults. If you do have multiple faults, you then have to look at maybe altering your voltage, so the more prominent ones you do first. So if you've got a step on it, and at 3 kV you see a big step, and then the next step isn't to 4.5 kV, try doing your testing at 3 kV. Because that means the fault at 4.5 kV, you may not be pushing so much voltage through it, so the one at 3 kV, you'll pick up a lot closer to it. If you've done everything at 5 kV, you're going to get a difference between the two faults. Okay. So this is just basically a little graph to show you. You're doing a 5 kV test. These are just recommendations. So sheath would be if it's greater than 100 microvolts per kilometre. If it is, then you do a pre-location. If you find a pre-indication, you can do your pinpointing. Now, you can do that in two ways. DC step voltage, which is this rectangular waveform, or we can do it with audio frequency. If it holds voltage, no action required. Again, what you will have is you will have some sort of test regime that should tell you this. Some companies do go by this sort of figure with amount of leakage per kilometre, which is okay, but then if you have a very long cable, you can have a bit of leakage in it naturally. So it's depending on what you will have some test regime which they tell you to do. The chances are it'll be 5 kV for 1 minute, and if it holds, all good, with no current. These are just recommended tests. XOPE, PE, and PVC. Chief test, generally 5 kV. Once you start going to the bigger cables, once you hit your 132s and your 220s, the chances are you'll a 10 kV. This is a recommendation test, duration 10 minutes. Again, these are just coming from European standards. You should have some test standards yourself. Majority of people, it's 5 kV for 1 minute. But that 1 minute usually is once the cable is charged. And if you look with the MFM 10, the time won't start until the cable has actually been all checked and the voltage is rising, then you'll see the time start on it. To give you an instance, that 255 kilometre cable I tested a while back, I had to go back and do some tests once the repair had been done, and we'd done an IR test on it. It took a 5 kV insulation and resistance test. This was an S1 that had 6 milliamps behind it. It took it 6 minutes to even get to 5 kV, and it took about another 7 or 8 minutes for the actual ohmic value to rise to close to 400 megohms. So these tests can take time. This 1 minute thing should be 1 minute from when that cable is charged and the current has dropped. Because before that, all we're looking at is we're charging something up. We're either drying it out, we're heating it up. It's a very long cable, it takes a long time to charge. Here we go, this is what we were talking about. So these are the two faults. So we've hit one here, and we've hit here. So if you get this, you've got multiple faults on your cable. Generally, if you've only got one, it will rise up. You may just get one little kink up, or more likely you get it up and then it will sort of fade off here. It will only hold a certain amount of voltage, and then the current will start rising. Right.
Back it up.
Sorry?
Go back to that page.
So this is showing you two faults. This is the first fault here, and it rises again because it's got the current to do this. It goes through, it starts rising again, and then there's another fault there. Yeah, you happy with that?
Yeah.
Right, pre-location methods. So we've got the HV measuring bridge, balance of the bridge, old school, good connection between the bridge and the cable, contact resistance. This is another thing that can have an influence as well. You've got to make sure that when you make these connections to either the core or the sheath itself, it's good, it's clean. If you start having dirty connections, there's a resistance there already, and that can have a detrimental effect on the result. So always make sure, when you look at the HV cable itself, the little clock clips slide onto the cable. There's little, like a little sleeve there that pushes back. If if you get a lot of sand and stuff in there, you can get resistance build up on that connection. You can get resistance build up where you connect to it. So you've got to keep these things clean, because if it's not, you can start getting spurious results. Equal resistance fault and auxiliary line. This is the 2-point connection. This is where we're talking your R1 is equal to R2 and R3. And then there's a volt drop method, which relation to the voltage drops in front and behind the fault itself. And obviously, pure Ohm's law is, we know what voltage it's holding, we know what resistance is there, so we know what the volt drop is, we can work out an ohmic value. Advantages of the volt drop method. Much less error sensitivity compared to brief-based methods, resulting in significantly higher accuracy for the pre-location results. Independent from resistance differs in sheath and core conductors. So you can use, you could use a conductor to send the signal up to the other end and come back on it. Where if you start using Glazier and Murray methods, they need to know the resistance going out. Well, you don't need to do that with the volt drop method. Independent from resistance of auxiliary wires, the quality of connection clamp has this effect, again, because we're not building up this resistance, we're looking at a volt drop. Automatic calculation of results without needing for additional entries. This is the old school one where we used to have to balance it, used to take the figures out, to make a ratio, and then go into an equation to give us a percentage, and then put it onto the cable length. Fast measurements, no moving parts, no calibration required, procedure required. So this is a basic look at it. This is for fault pre-location. Because we're using the volt drop method, we can use this core here, goes across, bridges through to there. The second connection, the white lead, again goes to the core here, goes through and connects to the sheathing, and then the black lead goes to the sheathing. So what we're doing here is we're looking at a volt drop here and we're looking at a volt drop here. And that's doing it on if you've got two cores. So you can do the core, so core there, and the core there, and that will look for a core fault. So if you have a lowish resistance fault on a core of a cable that you cannot use your surge generator on your van, your easy thump, whatever, you can use this to get a pre-location. It's basically how it works. So far end supply, far end sense. So voltage near. So it's looking at the volt drop there. And then we look at the far end. You can, on the unit itself, you can have this. What this is, it checks the connections. If you're doing core faults, it checks the connections for you. If you're doing a sheath fault, it tells you connected wrong. So if you're doing a core fault, you can switch this function on, and if you're not connected right, it comes up with this saying check connections. There's a connection problem somewhere. This is basically look at the screen. So this is your distance, which we set up here, and the voltage you're going to put through. And this is where we got negative near, positive near, negative far end, positive far end. So these different resistances here, it's slight, but it is enough to make a slight difference in the volt itself there. And then it gathers all the information up, gives you an average, and then it's say 20.1% of your cable length. Now, this is the important bit, is this here. This 20.1%. Not this, because if this is wrong, this is going to be wrong. This isn't. This is correct for the measurement. If you measure your circuit wrong, this result will be wrong. This result will always be right. But if you put the wrong distance in, you're going to get the wrong distance out. So it's always important to know the length of your cable, not the length of the route, because like we discussed earlier, is there a divert in the cable? Does it go up and down? Does it go over a river? Does it go over railway tracks? Does it go underground and dips down 6-8 meters instead of your normal meter? You know, all these has to be taken into account. So the best way you can do that is if you know the velocity factor of the cable. If you don't know the length of your circuit, you're only sort of guessing. If you know the velocity factor of the cable, you can use a TDR on it and get a very accurate measurement of the length of the cable. If not, as long as you're in a good ballpark figure, as long as the cable is 4,500 meters, you know, then you're quite close to it. But when you pinpoint, you can be tens of meters about this and then find it. If this cable was 4,000 meters, not 4,500, you're instantly over 10% out. So this could be 10% out. So that being 10% out, that could be 90 meters out. So this is the R1 and R2 relation. So this is looking at two faults. So there'll be two different measurements. Pinpointing. So what we're going to do, we're going to send out the step voltage. So what we're looking at is a ball of potential. So it's like a little sphere of voltage comes out from the fault. And these are what we look at. On for a second and a half, off for 3.5 seconds. Or on for a half second, off for 1. What we're looking at is we want a regular pulse. Because there's a lot of small voltages in the ground itself, what we want to see on our pinpointing unit, when we set this up, we get a pulse on the current and the voltage. What we want to see on our spikes is that we go on for a second, then off, then 1, 2, 3, on. So using this bit of kit, we want to see that sort of bar graph go backwards and forwards. So I think you guys are all familiar with the ESC, aren't you? You use it quite a lot, don't you?
No.
The spikes?
No.
No, you don't.
No.
Right. What this basically is, you've got a red lead, goes to the red socket, and a black goes into the black socket, and then the other end of that goes into these spikes. And what happens is when this voltage is at a high point, we should get either a red or a black, depending on what direction the voltage is coming from. So like this. So if you look here, this here is showing that the voltage is hitting the black lead first. So that means that's where the fault is. So you go towards that. And if you go past it, you'll get the red.
We use that sound for LV faults, you know, it's like some little idea.
That's right, yeah. I know the guys in, I think it was Leopardstown last time. I've done some training with the guys. I'm sure it was Leopardstown. We went out to a few faults. And you use it on those little LV ones that go up people's drives, don't you? And if there's a fault there, you tend to use that, because with the LV fault, by the time it's blown, the chances are it's gone through the jacket.
Yes.
It's exactly the same as, once the jacket is broken, it doesn't matter if it's a core fault or a sheath fault, we're going to get this little pulse. So the unit's just designed to pick up voltage in the ground.
Yeah.
So what we've got, so we're looking at this display, and we look at the voltage of it, and we just move closer to it, and you can see the signal rising. And when we go past it, it goes to red. Now you can use this for sheath faults or core faults. As long as the jacket is damaged, you will find out where that jacket is damaged. And even if it's a joint, and a joint's gone, if the joint's blown, you can sometimes blow through the joint or it comes out through the sides of the joint. You can put a voltage down it. So if you can't thump it, you can always use this as a way of pinpointing those sorts of faults. The way to check is disconnect the cable from earth completely and do a test from the core to earth, and if it's very low resistance there, you can use this method for pinpointing.
This is no good for some direct buried cables.
Sorry?
Some direct buried cables. It wouldn't be good for cable ducting.
No. Cables and ducting are a completely different kettle of fish. Problem with ducting is, once it's in the ducting, you've got to be able to get this voltage here to general mass of earth to get these spikes. Now, there is cables out there that have a graphite coating on it. So what would happen is if this was in ducting here, it creeps along and they do put conductive collars between the ducting. So you would pick up on a collar. So you could go to either side of the collar and you would know it's in that section. But to actually pinpoint on a sheath fault with ducting is very, very difficult unless the jacket's graphite coated and it has conductive collars on the ducting system itself.
We don't have them.
No. So it's virtually impossible to find.
Yeah.
Tony, you know that the lead that goes up on, you might separate the braid up onto a connection.
Yes.
Might have to air the semicon on the connector. Has that to be removed?
Yeah, because if you've got it on the semicon, it's still going to bleed through, isn't it?
Yeah.
What you'd have to do is completely disconnect. Anything has to be disconnected from earth, otherwise you've got a direct route through to it. What we're trying to do is we want the route to come through the general mass of earth.
Yeah. Alright.
This is just showing different directions. Some of the older pieces of kit have a meter on it, not so much just a bar graph on it, have a meter. So what you get is either one way or that way, and you can tell by the way the meter's going which is going. So what we're showing here is this is multiple faults. So if you're close to this one, you will see that way. But what you may get is if you're in the centre of two faults and the voltage is equal to each spike, you will get no movement on that graph, because what the graph is looking at is the voltage difference. So if it hits the black one first, you'll get more voltage here than you get here. If we've got a voltage leak here and a voltage leak here, hitting the rods at the same voltage, you will get no movement at all. What you would need to do is just move a meter to the left or a meter to the right and see if you start getting a pulse again. And then you would have to move to the next one. Don't immediately assume that you're on the fault if you know you've got multiples. And let's do it in C. I'm not sure if you guys do it in the C.
No.
On solid surfaces, you can use an A-frame, and if you've got an ESG with your piece of kit, it has
See the bag there, as far as I'm looking at.
Can you see this here? Yeah?
Yeah.
Well, what this is, it's a conductive pad. I went to a place quite a while ago, and I did some training with the guys on sheet modification. And I said to them, where's your pad, your conductive pad, because we was going on solid ground. They're all conductor pads, so they should come with some foam pads. They thought they were protection for spikes, and they'd thrown them. It's a conductive pad. If you put that up the spike itself, and then put a bit of water onto the solid surface, around here, you know, tarmac, paving, something like that, you can pick up the voltage. There you go, see he's got a couple wet rags. I tend to get a bit of water, from the bottled water, throw it down like that and put the conductive pads on it.
I never thought of pads before.
So the step voltage method, this is where we're sending this sort of rectangular waveform out. No wrong measurement by capacitive coupling. No interference by 50 Hertz. No change of the fault point by location method itself. So all we're doing is putting a step voltage through a little hole. Disadvantages, low sensitivity. If it's a very, very small hole, we're not pushing much voltage through it. So you go down to millivolts, and then you've got to be closer to it to find it. External voltages in the soil must be newly compensated for each case. Like we mentioned earlier, there is natural voltages in the ground, and that's why we look at this pulse of it. In the case of presence of several faults, highly resistive faults will not spark over, and the sensitivity will decrease. So it will put us between faults. So between the two biggest faults, it will put us between them. Burning. It has a burn function on it. If you have one of these really minor faults, that it's holding 4,800 volts, leaking very, very slightly, what you can do is put a bit of burn on it to try and open that hole up a little bit. Now, we're not sticking something on it for like 20 minutes. Do it for a few minutes at a time, leave it, then go back and do another test to see if that voltage is dropping. Because what we want to do is, if that voltage drops and the current goes up, that means the hole's a little bit bigger. The chances are we're going to get a better pre-location and we've got to pinpoint a lot easier. But this is always, after everything else, if you've done a test and it's a very high voltage, it's holding but still failing, and you're struggling to get a good pre-location, you've got a pre-location, you've gone out, and you can't pick anything up on the spikes, try a burn, just to try and open that hole up a little bit so we can get more voltage out of it. Any questions?
It's good for sheet faults on all voltages, Tommy.
Yes. Right, yeah. Can you see the MFM 10 in front of you? Yeah. Right, quick rundown. This is for an emergency box if needed. You can pull off from this and have an external on-off button, an emergency stop. This is your charging, mains and charging port. This is your protection button. And this bit here is where the HP cable goes in. Emergency stop, rotary dial, and acceptance button, on-off, interlock key, and then HD on and off. And then in here, you can put a memory stick to take results off. So we start on by switching it on. And what we see here is the version of the MFM boot, no software update, and then the next screen will tell you what version we're on, which is the 1.590, which I believe is the latest edition. If you ever have to update the unit, before you switch it on, put the update in the memory stick, switch the unit on. As it boots up, it will automatically update itself. So what I've done, just as a quick show, I've simulated a sheath fault, core fault.
So where did the updates come from, or when did it come?
Well, the updates,
Yeah.
they depends. If they find a patch, little tweak, they'll do it. I haven't seen a software update now for about maybe 12, 18 months.
Will we be notified that it's there? Or do we have to?
Yeah, what's the process for getting it to us?
No, all you need to do is, if the unit plays up, send me an email saying this is happening, and I'll check if there's been a software update. If you go to the Mega website, just mega.com, if you search MFM10 and it will come up, if you go to software, you can just download all the updates are always put on the website.
Right.
So if you're having an issue that something's not working right, or it's freezing, or just something doesn't seem right with it, chuck me an email, and what I'll do is I'll check to make sure that there's not a software update for it, and if there is a software update, I will let you know. I'll send you a link to it.
Okay.
Or if I get a notification, if I remember, I'll chuck you guys an email. But it's usually all the software updates for all our equipment is put on mega.com. Okay?
Yeah.
Right, what we've got, I'll quickly, if I can, this will work. It's just a rig up here. There's two cables here that I've soldered together. So there's a reeler cable here, which is about 16 metres, and there's a 25-metre reel here. So this is the solder joint here. So what I've simulated here is a fault, a sheath fault or a core fault. So down here, what we have is our connections. So the yellow connection's going to earth. The white connection's on a good core. The green connection's on a good core. And the black connection's on a bad core. Here, I've linked good core to bad core and good core to bad core. So if you look at the top of the unit, there's the drawings. Okay? What I've simulated is this. So I've got a black to good, white to good, green to good, white to good, black to faulty. So this is what I've simulated. So the first test we'll do is the test. So when we switch the unit on, that's what comes up immediately. So we accept that. Then it will ask us for test time and voltage. So if we scroll around to the little clock, click on that, and you can alter your time. So if we alter that down to a minute, accept, then we then accept the voltage. Then we can alter the voltage range to whatever we want up to 10,000 volts. We're only going to put 1,000 volts down because it's a little cable and we've got no need for it. So we then accept 1,000 volts, start the test. Green button. And what the unit does, before you'll see this, it won't actually start doing anything until it's done all its testing. It's thinking about it. It's sending a bit of voltage down, a bit of current down. It's checking to make sure there's a loop there. It's checking to make sure it's not dangerous for it to start up. And immediately, we've got 200 milliamps and no voltage. That's basically, we've got a fault. So, you can allow this to run for the 1 minute, just to confirm that it is a fault and we're not charging the cable up, that it's a very long cable. Because if it's a very long cable, you may get this, you may get a little bit of voltage and you may get a lot of current, because as we spoke earlier about, are we warming the cable up? Is there moisture on the cable? Is it a 200 kilometre cable that it's going to take a little bit of time to actually charge up before the voltage goes down? And as you see, it's done all its testing, it's figured out that we're okay, and now it's started the test. So always wait for this bit to start here, and not just put it on your watch, right, it's been a minute and switch it off.
So all the R phases in one duct, all the S phases in another duct, and all the T phases in another duct. Huge concentration of magnetic in each duct, whereas if you run RS and T in the same duct, the same thing what I was saying there about feeding the cables together, magnetic fields from each phase. Together there. So the cable heating up, that's power loss, like I said, 3 times now, so the cables run less efficiently. Then the safety reasons. Now, fair play if anyone gets this. What would the safety reasons?
Right, and that's the test finished. And what it will ask you, do you want to save the report? If you do, put the USB in here and press yes. If you don't, just press no. That's no. There's no USB in there, so it won't do anything. No, you've got to know. That's it. So we know we've got a failed cable now. So the next thing is we come to return here, this 9 o'clock position. So we return out and go to here, which is, if we look down there, pre-location. So hit pre-location. And what we've got here is sectionalisation. If it's got sections in it, we can put sections in it. And we've got distance, length of circuit. So here,
trace the cables, they open the ducts under the approved manner with their duct open tool.
let's see that small.
Maybe you use something like that, similar to that.
What we do here is down here, we can't quite see, just a bit.
Have a TDR, the coax leads,
Yeah.
they have given them.
No, but the shapes, for the shape for the one of the work. That's not the table hardly either. This is. Well, you must see.
Right, what we can see here is, if we click onto this,
That's obviously cancel and that'll come in handy.
Right.
we can alter the range. Now I've set this up to 350 metres because I know that this cable reel I have is around 35 metres. It's about 15, 16 on one side and about 25, about 10, 11 on one side and about 25 on the other side. So it's around the 350 metre mark. So we go back to voltage, so we set our circuit length up, go to voltage, we'll put 1,000 volts down because that's what we've done the initial test with. Press start, green button, and then we'll start seeing here our results come up. So what it'll start looking at is how much voltage it can put down, how much current loss there is, and the resistance of the circuit. So it's done all its pre-checks to make sure we've got all the connections right and it can actually see a loop. And as we can see here, it's just currents rising because we know we've got a fault.
This page here, you can see the specification of standard non-steam domestic underground service.
And there we go. 7 ohms resistance, 1 volt, and 198 milliamps. So now we're looking at negative DC near, 252 milliohms. And then we get a positive near, so it's 249 milliohms. And you look at that, negative 4486 millivolts and 4433 millivolts. Then it goes to far end, so that's on negative far end, 286. And then 290. So basically, this is all our measurements. And what it's saying is our fault is at 46.5% of our cable, which is around about correct, because that's roughly equates to 16 meters. So we've got 16 meters one side and 25 meters the other side. So we've done it from the other end. So that's basically showing us that's where our fault is. And if we look at the way we've got the cable configured, it's around about right. I haven't actually measured it. I just cut the cable up and soldered it on. But I know roughly how much I took off. Everyone happy with that?
Yeah.
Again, very simple. So once we've done that, we accept that, return out of it, and then what we do, we go to this icon here, which is pinpoint. So what we have here is, this is the cycle. So we come around to the cycle, and then we choose what cycle we want. I generally have it on this one here, 1.5 to 3.5. So if we set it to that, then if you go to the current one, the I, this should be set up as auto. So it automatically ranges your current. Now you can turn it right up or right down. So if you wanted to limit what current you do, but we tend to leave it and it automatically does it. So come out of that. And then voltage. So again, we range the voltage to 1,000 volts. And then start. And what we'll see is a rectangular wave come up. There we go. Because we know we've got a large fault, we're not getting much voltage out, but we're getting a lot of current. And this is where we will get that, the black and the red bar graphs. Then just go out with your spikes to the pre-location point and start looking with the spikes.
You know what, I've seen that as well, actually. Yeah, it's the same.
Okay, do you want to switch it off? And then you give it a couple of seconds and it automatically discharges. Everyone happy with that? Any questions?
No, all happy here, Tom.
Excellent. Any questions about anything else? And I can't name the winner of the 4:30 today. I'm not that good.
Tony, on the, you know, the strength of the magnetic trace on the listening gear,
Yes.
is the blue bar, I would say. Is it common that, say for long runs of cables out of stations, that magnetic trace will get induced onto another set of cables?
You won't get an induced signal onto it because that goes down as a magnetic pulse. So it goes down as like a ball of energy. So it won't get induced onto another cable. So if you've got cables running parallel with each other, you shouldn't. If the cable's sort of going like that, then split, the signal wouldn't go. You wouldn't get a signal go that way. It would only go that way. If you've got cables that are connected in parallel on a system, then you can potentially, as the ball of energy goes, where it's on the system, it can split going that way. So
So we
So
left our,
if you have parallel connected cables, then yes, it would. If you don't have parallel connected cables, just parallel running in the trench, then no, it won't.
yeah, so if we don't disconnect our screen wires, let's just say on the MV, that there's a possibility that you could get a bit of a magnetic trace on other circuits.
If your screens are connected together, you are putting the surge down the core. So it wouldn't. It would only be the return path it would come back onto, and then you're connected straight to the unit anyway. So even if screens are connected together, it wouldn't make any difference because you're putting it down the actual core itself and not the screen. If you were thumping a screen, then yes, it could separate. But if you're not thumping on a screen, you're thumping on the core, then no.
Okay. Thanks.
So how would you explain, Tommy, that sometimes we would pick up a magnetic trace on a different cable that we know is in a different location?
Depends how it's connected. If you have got the screens connected together and that's before the unit, then the return signal can go onto that screen. That would only be the screen though. It wouldn't necessarily, you may pick up a slight bit of magnetic, but you wouldn't get no acoustic, so you wouldn't get your clear numbers.
Yeah, but it would
that magnetic signal you can pick up spuriously anyway. You can go out onto the road, even if you're not on the cable you're thumping, you will pick up a magnetic. You will pick up some sort of magnetic. But you won't get the acoustic. When you look at the two bars, you have to have that little dot down here and a little dot down there. So it hits the magnetic, then it hits the acoustic.
Yeah.
If you just get the magnetic, then you're not picking up the surge you're looking for. That would just be some magnetic you've got somewhere in the cable or somewhere in the ground.
Yeah.
You have to have that magnetic and the acoustic and get that black number and not a grey number. As long as you get that black number, you're picking up magnetic and acoustic, and that should be the cable you're on. Magnetics you can pick up anywhere. There's these magnetic pulses all over the place, going through different cables, going just generally in the ground, and you will pick them up. Okay, gents, anything else? No? Everyone happy?
Well covered, Tony, yeah? Thanks very much.
No problems. Any questions or anything you come up with, or go out and use the kit. And in a couple of weeks, if you find that something's not quite right, either chuck me an email, or maybe we'll have a meeting again in a few weeks just to look at how happy you are with it. And as soon as I can get over to you, we'll come out with some practical sessions actually out on site and use the equipment properly. And any issues you've got there, we can cover it then. Okay, gents?
Right.
What's your email? What's your email address, Tom?
Sorry?
What's your email address?
Tony.walker@mega.com. And any issues you have with fault locating, even if it's not with this bit of equipment, just chuck me an email. And
So you have to be on your inbox in the morning.
Yeah. All right, again, if that's it.
Thanks very much, Tony.
Thank you, Tony.
No problem. Any issues, just give me a buzz.
All right, all the best. Thanks, everyone. Bye.